In the previous few chapters, we took a look at what kinds of distributions are possible for our datasets. Now we want to be able to go through summarizing quantities about our distributions. Basically, how can we summarize and describe our distributions, as well as see how distributions can be applied in real life, specifically the normal distribution. So what are we going to go through this chapter? First, we want to understand how to summarize different quantities to describe a distribution. Then we want to figure out the moments of a distribution and how to find them. We then will take a look at what the central limit theorem is and see how we can apply that to a sampling distribution to approximate our sample set and our data set as a normal distribution. So the first thing we're going to go through is how to describe a distribution through certain quantities called its moments. So we won't be expecting you to be able to apply the moment generating function. It would just be important to know what moments are used to describe a distribution regularly. Afterwards, we'll take a look at a Gaussian distribution in real life. Two really good examples would be the Maxwell-Boltzmann distribution for speed in ideal gases. And then we take a look at the distribution of stellar masses in young star clusters. That would be a good example of when you don't have a regular normal distribution, but you can log something to make it a log Gaussian distribution. So first, we're going to go through summarizing quantities for a distribution. We'll start by reviewing measures of location, measures of spread, and then go into percentiles. So first of all, we've gone through this already. The mean, median, and mode are very popular measurements that describe our data set and the location of our data points. The mean is going to give us the average of our values, and it's going to give us the most common estimate of a distribution's location. So for a population, we have mu is equal to the integral of a weighted average. For our sample set, we have an average mean of the sum of all points divided by the total number of points that we have. Keep in mind, as n approaches infinity, our sample mean is going to approach the population mean. So for Python code, we can simply calculate the mean through three different methods. If we're simply using a data set, we can use the mean function from NumPy. If we're trying to take a look at a mean of a large set of values, you can also use the mean function from the statistics package. And in most cases, we'll be using SciPy stats. So in that case, if we already have a distribution ready to use, we can simply use scipy.stats. Whatever distribution you have, like a normal distribution, and then .mean to calculate the mean from that distribution. So whether it's Poisson, whether it's Maxwell, whether it's a continuous distribution, you can apply that mean function to any distribution in the SciPy stats package. Then we have median and mode. Those are less common when we're taking a look at distributions. We have median, which is the point at which half the values are above and below the point. We then have mode being the most probable value, which is sensitive to binning. So let me explain that in a bit. The Python code for median is fairly straightforward. It's median from NumPy, median from statistics, and you can also use the exact same thing, median from your distribution from SciPy stats. So these two are going to be the ones that we use the most. Now for the mode, it really is sensitive to binning because the most probable value will be highly sensitive to how many bins you have. If you have less bins, then your mode might be a little bit less accurate than you want it to be. If you have too many bins, then it's very difficult to take a look at the mode or to see a clear trend. Now, if you have a set of values, you can easily calculate the mode by using the mode function from statistics. Otherwise, you would have to code it yourself. So now let's take a look at measures of spread. So we have gone through this before, but we can take a look at standard deviation, which is given as sigma for a population and s for a sample. And that means we can define variance, which is the square of standard deviation, as follows. So I won't go through these two equations again. They're just presented here to remind you of the two equations that we've used for population and sample variance. So apart from that, let's now introduce a new term called the coefficient of variation. So it's called CV or RSD for relative standard deviation Through this, we get to see how close our sample is to our population. That CV is a dimensionless ratio of the standard deviation to the mean of a distribution, and it's given as follows. So you have your sample divided by the mean. And it's very, very useful in expressing the precision or the repeatability or reproducibility of your experiments. It basically helps measure the spread of a population's distribution around its mean. Just be careful when you use it though, because it only holds meaning. It only holds meaning if you have a ratio scale. So those that have a meaningful 0 are going to allow for a good comparison of two measurements. So for example, if we take a look at the temperature scales, Celsius and Fahrenheit, their zeros are going to start at different spots, and so they're not really a good comparison. But if you were to use Kelvin temperature, where you have absolute 0 at exactly k equals 0, then you'd have a meaningful 0 and have a ratio scale to compare with between two population and two distributions. So just keep in mind, when you are using the coefficient of variation, you're going to try and compare your distributions with each other. So in that case, it is very useful to compare if you have the same 0 for each one. So percentiles help to measure the value below which a given percentage of observations are going to fall. So we can integrate the area underneath a probability function to find the probability of values falling in between A and B. So if I want this to be A at minus 2 sigma and plus 2 sigma to be B, then the probability of our values falling in between minus 2 sigma and 2 sigma are going to be a cumulative area between these 2 points. So when we talk about the percentile for a probability distribution, it's not really between A and B. It's going to be an interval or a specific point, in which case you have all the values before that point, and then your upper values after that point. So you have the 99th percentile, for example. This is going to be a value where 99% of your values are going to fall before that. So that would be here, a percentile of 99. If you want a percentile of 90, let's say, then you're looking at a certain standard deviation away from the mean. So in many cases, we would want to figure out the percentile to try and find out a certain level of confidence in our measurements. Regularly, you would use a 95 percentile to represent a 95% confidence interval, let's say, and that's going to be equivalent to a 1.96 sigma or 1.96 standard deviations away from the mean. So these are things that we'll talk about in a future chapter. But for now, just note that the percentile for a probability distribution is going to give you the value at which point X% of your values are going to fall before that, and the remaining will be after that. So it's kind of like a division of where the points are. If we want to figure out how to code this through Python, you can use the percentile of a certain value to figure out what that value is. You can also use, for a distribution, SciPy stats, and you can use CDF to get the total percentage, the total number of values up to a certain point. So moving on to moments of a distribution, I want to go through expected values, a moment generating function, as well as the 4 main moments of a distribution. So expected values, let's call them E to make things easier. It's called the generalization of a weighted average of a random variable. It's going to be defined as the mean of a large number of independently selected outcomes. So what does this mean? It basically means your expected value is going to be the mean of your X values or your X variable. And so that mean is going to be calculated after you sum up all of the expected values multiplied by their probability. So we can say that the expected value of a variable x is e of x, and usually that's going to represent the mean because it's the most likely value to take place. So if we have a discrete data set with a probability mass function, we're simply going to calculate the weighted average to find ex, and we'll find that usually that first value is going to be the mean. So if we have a random variable x with a probability density function, which is now continuous, given by a function px, then we can calculate the expected value as the mean of all this, or it's going to go from minus infinity to infinity of x of f of x dx. Keep in mind there's a negative here. Apart from that, once you do have the mean, we can calculate the variance. And so the variance is going to be the expected value, which is going to be some sort of mean approximate to your actual true mean minus the mean that you get squared. So that will give you the variance and a measure of spread from your sample mean to the expected mean. Now, moment-generating functions, they're a bit more complicated. A moment-generating function helps us to determine the distribution of a random variable. But keep in mind, a moment-generating function simply will allow us to describe that distribution. So how do we do this? We call it the MGF. The MGF of a certain random variable x is going to give us all the moments of x. So that's why it's called a generating function. It generates the moments for your function. The MGF is going to determine the distribution of a random variable and allow us to compare one variable to another. So first, we know that the first moment is the expected value, ex. So we're going to define the MGF of x as a function, mxs. So that means the moment of x given your sample, as follows. So the MGF of x is only going to exist if there is going to be a positive constant a, such that your value is finite for all s values. So in this case, we're going to keep the explanation short. If we can set up a moment-generating function as such, and we define the moment by an equation, let's just assume it's e to the power of sx, then we can expand the exponential function here and get this from our Taylor series expansion. We can replace the x with s times capital X and get an adjusted or modified version of the Taylor series expansion for this particular function. And then we can define mx of s as follows. So this is the summation formula for a moment-generating function. So as you can see here, we can conclude that if you have a kth moment of x, then the coefficient itself, s to the power of k over k factorial, we can use these coefficients to generate different moments for our function. So in terms of generating these moments, I will be uploading a separate document onto our course website that will go through a detailed overview of how to derive each of these moments from that initial equation. But first, I want to explain that there are 4 different moments here, and there are different types of moments, and the calculation is different. So the first raw moment we already discussed before. The moment is going to be an indicator of how far something is away from the mean. So the first raw moment gives us exactly that. It gives us the mean. So mu is equal to ex, the expected value of x. That makes sense. So we say that the raw moment is going to be one around the origin, c equals 0. So that gives us the moment about the origin of what we're measuring. Now we have another moment that's commonly used. We call it the variance, and that does help us describe a distribution. So this is no longer a raw moment. It's a central moment about the distribution's mean. So we try to see how the data varies around that mean to see if there's any skewness taking place. So that leads us to the third moment, which after deriving it again, you would notice that it's no longer a central moment. It's what we would call a centralized moment. A standardized moment. So a standardized moment is going to be a central moment that's normalized by the standard deviation. So after you apply that modification, then you can determine the skew of your distribution. So that will help us measure the relative size of the two tails of the distribution. So if there is a smaller tail on one side and a larger tail on the other side, we know for sure that the data set is going to be skewed towards the right, because there's a higher quantity of values towards the right, giving it a bigger tail on the right side. So that helps us define skew. From that, we can also define kurtosis. And keep in mind, skew has everything to do with the spread of data. So you're really looking at the tails to see how far they spread. Now, if we take a look at kurtosis, it has to do with how many data points fall within those tails. So if there are less data points within those tails, then that means that you're going to have a sharper peak and more data points in the center. If you have more data points along the tails, then that means that there's going to be less data points distributed throughout the peak, which means it gets a little bit more rounded. So that measures, kurtosis measures the combined size of tails relative to the whole distribution. So it makes sense that if you have more tails that determine and define your entire distribution, then your peak is going to be less sharp. So just be aware that kurtosis, even though it does describe the peakiness of a distribution, the true definition of kurtosis is really going to be how the tails are distributed, how the data is distributed throughout the tails compared to the rest of the distribution. So here's just a little bit more information about skewness and kurtosis. With skewness, you have a level of asymmetry that deviates from a normal distribution. So as I said before, those standardized moments have everything to do with tails. If you have more data points on the left or anterior tail of your distribution, you have a negative skew because it's skewed towards the left. There's more data points towards the left of your peak. Now, if you have a positive skew, it means that your right-sided tail is going to be longer, and so there's going to be a larger amount of data that's towards the right of your distribution. With kurtosis, we have the peakedness of a distribution, but just remember, even though it's easy to remember kurtosis as how sharp a peak is, that's not its definition. The peakedness is going to come from the distribution of tails, which will affect how sharp your peak is. So let's take a look at these three distributions here. The blue one is one that has a sharper peak. So that means it's going to have less values along its tails. So therefore, we call this a leptokurtic distribution. We then have a normal distribution in the orange. And if you have more data points spread out along the tails, then the peak is going to decrease naturally. And you have a platykurtic distribution. So from Python, there's two different easy ways to calculate the skewness and the kurtosis of your data points. You can use the functions themselves, just skew and kurtosis, directly from scipystats. But if you do have a known distribution, like a normal distribution, exponential, binomial, and so on and so forth, then you can just define m, v, s, k as variables and set them equal to your distribution name, .stats, and make sure you use moments equals to mvsk. So that will give it the first 4 moments of the distribution saved in each of these variables. So just make sure that you know how to calculate and figure out the different values for skewness and kurtosis for different types of data sets. Okay, so now let's talk about the central limit theorem. This will be fairly short, but the central limit theorem is very, very powerful and very useful in making approximations to our sample distributions. So let's first start off with what a sampling distribution is and what the CLT is. So far we've talked about taking measurements of random variables. And so the type of random sampling is how a sample is selected via experimental design, which we'll cover in the next chapter. But when you select a random sample from a population, the numbers that you get from it and the data points you get from it are called statistics. So that means if I calculate the mean of my sample set, then I have the mean as a statistic. If I make inferences about that statistic, and then I can make assumptions or predictions about the mean of a population, which then becomes a parameter. So keep in mind, for a sample, we use mean, median, and different measures as statistics that we can analyze. Once we analyze them, we're making guesses about the parameters of the population. So you'd be looking at comparing your sample mean, which is a statistic, to the population mean, which is a parameter. So the sampling distribution of a statistic is going to be the probability distribution for possible values of that statistic when you have random sample sizes of n being repeatedly drawn from the population. Now, that's simple to state. When you collect data and you have a bunch of measurements, you're going to get a sampling distribution. Now, the central limit theorem says that under general conditions, if you have enough data points and your sample size is large enough, it doesn't matter what that distribution is. It's going to approximate a normal distribution. So that is very, very useful because then we can very easily model the randomness and the distribution of different variables. So the CLT basically says the sums and means of random samples of measurement from a population tend to have an approximately normal distribution. So that means that the sampling distribution of the sample mean, we can have a standard deviation of the mean being equal to the standard deviation divided by the square root of n. That is just simply going to give us the sampling distribution of the sample mean, which we'll use in the future for standard error. If the population has a normal distribution, the sampling distribution of x is going to be exactly normally distributed regardless of n. So from the CLT, if we have a population that has a normal distribution, then your sampling distribution of x should be the same regardless of how many measurements you take. So that means if your population already has a normal distribution and the measurements you take represent that, then you should have a normal distribution from your sample set as well. Now, if your distribution is non-normal, which is very often the case, what you'll find is that as you increase the number of sample and measurements that you take, your sampling distribution of x will be approximately normally distributed. So the CLT basically says that if your distribution is normal, then great. It's already at a normal distribution. You don't have to approximate it. But if your distribution is not normal from the beginning, then if you apply the CLT and if you make sure that you have enough measurements taken and n is greater than or equal to 30, you can immediately apply the CLT to approximate it as a normal distribution. So the next slide will kind of explain this in a little bit more detail. What does the CLT tell us and how can we use it? So no matter what distribution you have, what the CLT tells us is that the shape of the sampling distribution will approach a normal one as the sample size grows. So increasing your n will also help reduce your sampling error and will also allow you to make a better estimate for your population mean, which is a parameter. You can also use this to predict other parameters like standard deviation. So here's an example. If I take two measurements and I bin my results between 0 and 1, then I simply have this as my distribution, there's not much of a distribution at all. If I split up my measurements between 0 and 1 and create an interval, and I take more measurements where n is equal to 5, then I get some sort of a distribution here. As I increase more and more measurements, then I get a more normal distribution, and that's when you can apply the CLT to say that, well, I have an approximately normal distribution from the measurements that I've taken. So it's logical here to assume that the more skewed and asymmetric the original distribution, the more and the larger your n value would have to be to get it closer to a normal distribution. But in most cases, especially for this course, anything past n equals 30 is when you can apply the CLT. So now we're going to go through where we see Gaussian distributions in real life. I want to go through the Maxwell-Boltzmann speed distribution and just another example of something that happens in space with the distribution of stellar masses, and to show that even if you don't have a perfectly normal distribution at the beginning, you can modify it slightly to get to a Gaussian distribution. So first of all, where do Gaussian distributions take place in real life? Pretty much anywhere. A normal distribution is called normal because it happens under normal circumstances, especially after you take many measurements of something. So some examples of normal distributions in real life: average human height, average weight of newborn babies, shoe sizes from birth, test scores, usually if there's no other things affecting it, average blood pressure for men versus women, rolling a dice as well, because you can get certain expected values from that, a coin toss, and that would give you the probability of getting ahead for all tosses. In the middle of the distribution, you have a 50% chance of getting ahead, and that's going to be the highest one. So that is a very normal distribution. You can take a look at the random motion of particles, measurement error from experiments, especially random errors, as well as the concentration of specific ions from within your body. So in that case, there are so many different examples of normal distributions in real life. We're just going to take a look at two of them. So the Maxwell-Boltzmann probability distribution is very famous. It's very popular in statistical mechanics, as well as in chemical physics. So what does it tell us? It basically is a distribution. It's a probability distribution that describes the distribution of particles in a system at different energy levels. So if we take a look at a specific energy level, then it's going to have a specific set of speed distributions. So this distribution in particular is something called a chi distribution. And what a chi distribution is that it takes into account a set of independent random variables, and each of them follows a normal distribution. So since the MB distribution has everything to do with particle speeds in an idealized gas, that means there's 3 independent random variables for movement in the x, y, and z direction in 3D Euclidean space. So therefore, you're going to get 3 degrees of freedom when you're working with the MB probability distribution and speed. So the Maxwell-Boltzmann distribution itself is going to be a result of the kinetic theory of gases, which applies to the classical ideal gas. So with the MB distribution, we're trying to determine the speeds of particles within an ideal gas. In real life, though, remember this is just a model. In real life, you'd usually have van der Waals interactions, quantum exchange interactions, and other effects that could affect the speed distribution and allow it to deviate from a normal distribution. So in this case, we're looking at a simply idealistic situation where nothing affects the speed except random motion. So the probability function is then given as follows. M is going to be the mass of the molecule in kilograms. You have Kb being the Boltzmann constant. You have T being the absolute temperature, and V being the velocity, which can be further split into its components, Vx, Vy, and Vz. So we won't really be going through this in the course. You'll learn a lot more about it in stat mech in the future. But the most important thing is we can model this through SciPy stats. They actually have a built-in Maxwell function that allows us to model the distribution very easily. So here's an example that I grabbed from Wikipedia, I believe. If we want to visualize the Maxwell-Boltzmann probability distribution, it looks kind of like this. It's got, it almost looks like a normal distribution with a skew. So it's skewed more towards the right with more data points kind of tapering off this way. And of course, at different energy levels or for different types of molecules, you're going to get different curves. And of course, at different temperatures as well. So in this example, we're going through different types of molecules. In the assignment, we're going to go through different types of energy levels or different temperatures. So here, the Maxwell-Boltzmann distribution essentially tells us that as your particle size gets larger and larger and heavier, you have a sharper peak over here, and then the density of moving, or the probability of moving at lower speeds is more likely. So that makes sense. And the higher, or the smaller your mass, the more chance that you'll have a fairly normal distribution amongst all possible types of speed. So let's take a look at the next one. So that's the Maxwell-Boltzmann distribution. When we're taking a look no longer at the small scale or molecular scale, let's take a look at the large scale side of things. Let's take a look at the distribution of stellar masses in different stars. So research has shown that the distribution of star masses found in two different young star clusters agree well with each other. So basically, I grabbed this from a textbook and an article. These black dots represent the stellar masses for one particular star cluster, and the gray dots represent the mass distribution for another star cluster. So just comparing the two of them, they correlate well with each other. It looks like it tapers off at approximately the same slope. You'll also notice that it kind of goes up over here. And this over here has already been reported by the researchers to represent incomplete sampling. So these masses are too small to really continue with. So they've treated them as primarily outliers to the situation. So looking at this, we know that it doesn't look like a Gaussian distribution. It looks more like an exponential decay. So what can we do to try and model this using a normal distribution? So the next step would be to take a look at the log Gaussian. If a distribution doesn't look Gaussian, we can usually take the logarithm to form what we call a log Gaussian. And using the same data as before from the previous slide, we get this distribution. So we replot everything. We make sure we have a log-log graph, and we'll be able to see that we have a fairly normal distribution between two data sets, and they correlate quite well with each other. So in that case, in many cases in nature, you'll be able to find situations where even if you can't see a normal distribution right from the beginning, some manipulation can get you there if it's done properly. So just as a summary, what we have to know from this chapter, you should be able to define and determine the different measures of location and spread. You should be able to understand what percentiles are and how to calculate them. And of course, you should be able to use Python to find the mean, variance, skew, and kurtosis of a distribution for any distribution that's given to you. You should understand what the central limit theorem is and when you can apply it, basically when n is greater than or equal to 30. And you should be able to understand that Gaussian distributions are very popular in physics, and that we went through two examples where they're quite common. Maxwell-Boltzmann distribution, and even masses of stars. So in the next few chapters, we're going to take a look at error analysis and experimental design, moving towards complete data analysis.